Hi everyone, I am Matan and I'm a PhD student at the Weizmann Institute of Science. I'll present our work named SAL, Agnostic Learning of Shapes from Raw Data. This is a joint work with my advisor, Yaron Lippman. Recently, neural networks have done a good job in learning 3D shapes, but one popular approach for representing shapes is by surfaces. In particular, implicit representations, where the idea is that a surface is defined as a level set of some volumetric function. One option is to define the implicit volumetric function over a fixed grid. The second option is that instead of working with a discretized ambient space, we can use a neural network to model a continuous volumetric function. Then the shape is defined as a level set of a neural network. I will refer to this type of shape modeling as implicit neural representations. So for training, what previous work suggested is to treat it as a regression or classification problem. That is, training is done on samples of points in space using supervision about each point, indicating if it's inside or outside the shape. Extracting these samples for regression is possible when we have 3D supervision. However, what about raw 3D data such as point clouds? Trying to proceed with the same approach introduces the question of how to determine for the regression sample points if they are inside or outside the shape. Clearly, this is a hard question with many possible solutions. However, we suggest a deep learning approach that overcomes this issue as part of the learning process. So here we see an example for the type of data we would like to directly train on. These are human scans from the dynamic fuzz dataset. Each scan is a triangle soup where common defects include holes, ghost geometry, and noise. Back faces are in blue. So now, let's try to understand our method by considering this two-dimensional toy example. As we are working with raw data, we can only utilize unsigned information, such as the L0 distance to the point cloud. That is 0 on the point cloud and 1 everywhere else. Another option is the L2 distance to the point cloud. We will generally denote an unsigned distance function by h. Clearly, regressing a neural network f to approximate any unsigned distance function h does not yield an implicit surface. In more simple words, the neural zero level set would concentrate on the given point cloud and does not connect the dots in some plausible way. So we suggest the following simple idea. Given the unsigned distance function h, we suggest a loss function that encourages the neural network f to approximate h while being agnostic to the sign. That is the role of the function tau. Here is some particular choice for tau. Note that one could come up with a different choice for tau as long as some reasonable properties are satisfied. So let's understand what this choice of tau does. Let's consider a simple one-dimensional example. Given a single point x0, here is the unsigned distance function to x0, h. And let's assume that the neural network f looks like the red curve. So in this situation, our loss strives to minimize the white area, and f would converge to the signed distance function to x0, which is a good thing. That is exactly what we were looking for. So we see our SAL loss introduces a new desired local minimum. However, it depends on how the network f is initialized, as the unsigned distance function h is also a possible local minimum. To address this issue, we derive the following network initialization, which is crucial to our algorithm. However, it's only a slight modification over existing initialization schemes. A neural network initialized with our geometric initialization is approximating a spherical signed distance. Going back to our 2D toy example, after training with SAL, we can see that we are able to converge to plausible neural implicit representations. So now let's go over some of our experiments. For learning a shape space from the dynamic Faust raw scans dataset, we use a variational autoencoder. And here we can see our results. Test scans reconstructions are the right shape on each gray pair. Golden shapes are generated by latent space interpolation. In fact, SAL can also be trained on a single raw point cloud. We qualitatively compare SAL to non-deep learning implicit surface reconstruction methods, and here are the results. So thank you all for listening. I'll be happy to discuss our work, so please reach out. Thanks again.